I'll talk about astrophysical black holes, and one subtitle that I could take to this talk is From Darkness to Light, because one big puzzle about black holes is, even so their name involves black, and we all know that they don't emit any light, they're usually at the center of the brightest objects in the universe. So there's a puzzle, but it's a good puzzle because of this situation we can actually study them. And I will focus about two questions. The question is, are there black holes in the universe? And how can we verify that? I still remember when I was asked about the average age here, and I gave a talk somewhere, it was Amherst, I think, about my work on some model involving black holes. And at the end of my talk, one of the distinguished members of the faculty came to me and said, well, it was a very nice talk, but I don't believe in black holes. I don't think that even if this would have been today, he would have dared to say this. These things have changed in the last 30 or 40 years. But the question is still there, are we really sure that we see black holes? And I'll try to address that and try to see what should be done to be really sure. So the old ideas about how to find black holes I think they go all the way back to Michel. And he suggests how to find a black hole, or it's either Michel or Laplace, one of them. You just look at the sky, and eventually a black hole will pass in your line of sight, and you will see something, some dark point, and you will know that this is a black hole. Now, since then, this was in the end of the 18th century, or 17th century, millions of hours have been used on various telescopes, and no one has seen this picture. So this is not a good way to find a black hole, and you will see why in a second. Even so, you will see that we are getting close to that, but not yet there. So what are the other ways? The other ways is to use the fact that black holes are actually in the center of bright objects. And in fact, this is how we got to the first black hole. This is Cygnus X1, the first black hole candidate. It's an X-ray source sitting in the Cygnus group, Cygnus constellation. And we can see it in X-rays. It was first detected by rocket in X-ray in 1964. It was then detected in radio in 1973. The radio detection was extremely important because the X-ray detection was not accurate enough to pinpoint where it was. But the radio detection was. And once the radio detection was there, the companion was discovered in 1973. And once the companion was discovered, we can learn what is the system. Because it was realized that this is not relevant here. This is the companion, the brightest star here. This is the companion. It's a massive star which is turning around the companion, the dark companion that we don't see in optical light at about 5.6, at a period of 5.6 days. Now, when you have these observations, you know the period, you have a binary system, you know the period of the rotation, you can measure the velocity of the companion by the Doppler shift. So you have P and V. G, it's a Newton constant. So you have the mass function. And this is the mass function for the object, the unseen object, the object that you don't see. And it's just simple Newtonian dynamics. Nothing goes into this formula. You can derive it at high school or definitely at first year of university. So you have this relationship. And this mass function equals to the mass of the object that you don't see times sine cube I. This is the inclination angle of the system. You see only one object. You don't know if the system is like this or is like this. You don't know the plane of the system. So you have a factor here, sine I, that you don't know. And you have 1 plus q. Q is the mass ratio between the two stars. But if you look at it, if you put this 1 plus q up here and the sine I down there, then 1 plus q is always larger than 1, and sine I is always less than 1. So if you evaluate this factor, you get a lower limit on the mass M1. And the lower limit from the dynamics on this mass of Cygnus X1 was that it's around 10 solar masses. And if you put some more reasonable values, then it could be probably somewhere between 10 and 20 solar masses. And between 10 and 20 solar masses, you will say, aha, this is probably a black hole because it couldn't be anything else. How do we know that we couldn't be anything else?
What was the way that you determined it from the X-ray and the radio?
No, this determination is from the optical.
I know, but
All this was not known. All this was not known when you had just the X-ray or just the radio. The moment that you had the radio, you could know the exact position. The moment that you know the exact position, you can determine who is the companion.
the radio, there is a suspected black hole.
You associate the radio with the X-ray. You see the X-ray is the same position as the radio. Then you go to here. By now, you don't need the radio. By now, the X-ray is good enough to go directly to the X-ray. But at that time, it was impossible. So all this depends on the optical observations. Now, how do we know that this is not a neutron star? Because what we see in the X-ray, we believe that what we see in the X-ray is matter falling onto the compact object, to the black hole, and we see the emission from this matter which is falling onto the compact object. But we also know, and we also see other systems in which there is a neutron star, and we know that there is a neutron star there, and these neutron stars also emit X-ray and so on. So how do we know this? We know because there is a maximum mass for the neutron star. We heard in one of the earlier talks by Gary the remark that the maximal mass of a white dwarf, the Chandrasekhar mass, is about 1.4 solar masses, and there is a corresponding mass for a neutron star. The issue is that in a neutron star, the situation is much more complicated. In a white dwarf, we know exactly the equation of state. So there is no game that you can play. And once we know the equation of state, we can solve the equations with precision, and we know exactly what's the maximal mass. With neutron stars, because the density of the neutron stars is about 10 to the 14 grams per cubic centimeter, it's about the same as the density in the nucleus of an atom. Nuclear actions are important. And you have to take into account the strong and weak forces, and there are a lot of unknowns there. And just to demonstrate the level of unknown, these are a relationship between mass and radius of neutron stars for different equation of states. And all this equation of states are very good physical justification. So you can see that we don't really know what's the equation of state at very high density. And there are all kind of speculation that very high density you can get to a quark phase or a strange star phase or whatever. But the important thing for our purpose is that it doesn't matter. All these equations, even the strangest ones, have an upper limit of about 2 to 2.5 solar masses. This is the upper limit. You see all these equations, you have this M-R relationship, but M saturates, and this is the maximal limit that the neutron star can have with different equation of states. Some of the equation of states here, for example, all these equation of states are ruled out now because we have a candidate, which I'll show in a second, which we know that's a neutron star which is more massive than 2 solar masses. So this can be eliminated, but there's also some more general arguments saying, for example, suppose that we don't know anything about the equation of state, but we just use causality, or we just use that the pressure is finite, or we just use this or that, so making various simplifying assumptions, and we always get some limits which are around 2 to 3 solar masses, maybe 5 solar masses if you really push. So when you get to 10, it's really something else. But still, it's not really a proof that we see a black hole, because all that we have proven so far is that we see something else, that it's not a neutron star. It may be something else which is more compact. Okay, this is, by the way, the heaviest neutron star. It's a pulsar, and the determined mass is 2 solar masses. It's amazing the way that this mass was discovered. So it's a side track, but an extremely interesting one. This is a system in which we have a pulsar and a white dwarf, and the two objects are almost in the line of sight. So the pulses of the pulsars that comes towards us at certain phases of the orbit come very close to the white dwarf, and then what we have is a Shapiro time delay. We have a time delay of the pulses because of the fact that they are passing in the stronger gravitational field. We measure this time delay. From this time delay, we have sufficient information to determine both masses, and this is how this guy is, the mass of this one is realized. And it's a very important realization in terms of structure of neutron stars. As I've shown you before, it eliminates a large fraction, many candidates, and it has some other possible astrophysical implication, the fact that you can have such a heavy neutron star. Mind you that a very interesting open question is not just what is the maximal mass of a regular neutron star, but what is the maximal mass of a rotating neutron star, because when you add rotation, you can increase the mass further, not by much, but it could be 30 or 40%, and this could be important in some astrophysical modeling. So, okay. Let me jump to another topic, which is very relevant here. We have a black hole. We suppose that we have a black hole in Cygnus X1 or in one of these other accreting systems. And the metric of the black hole is expected, the black hole is expected to be rotating. I'll show you actually that we can shown to be rotating. So the metric is demonstrated by, given by the Kerr metric, which is the stationary metric for rotating black hole. So this is the metric written up here. Miraculously, the equation of motion is integrable. Two constants are trivial. This metric does not depend on t, and it does not depend on phi. And because it does not depend on t on phi, then it is immediately follows that the energy is measured by an observer at infinity E, or the angular momentum is measured by observer at infinity, are constant of the motion. This comes automatically, but it depends on theta. Miraculously, there is, because of some algebraic connections in this metric, there is a third constant, which is called the Carter constant, which is Q. It's called Q after Carter. And this Q is a quadratic constant. It's not, these two are linear in the momenta. This is quadratic, but it's also conserved. Once we have three constants of motion, we have also a fourth constant of motion, of course, which is mu, the mass of the particle, which could be zero if it's a photon. So this also describes trajectory of a photon. So with the fourth constant, we don't need to actually integrate the geodesic equation. We have basically a closed form for the velocities. And the problem really reduces to something like the motion in Newtonian potential, but slightly more complicated. Most important is the radial potential, which determines the radial motion. And this is roughly for a constant angular momentum. This is the shape of the potential. You can be above this line. The VR is positive, so you can be there. You cannot be below this line for this E and L. So what you see here, that you have a minimum here. This minimum corresponds to a circular orbit. You have another maximum here. You have a maximum here. This maximum also corresponds to a circular orbit, but this one is an unstable one. And if it was a Newtonian potential, this would have gone all the way to infinity with the potential centrifugal barrier. But here, because of the complexity of relativity, this goes down. And so you fall into the black hole if you are, even if you have angular momentum, but you can fall into the black hole. The most important thing to remember here is that there is a critical angular momentum for which you will have a critical minimal circular orbit. This is called ISCO or RMS, depending on whom you want to talk. This is because MS stands for marginally stable orbit. So this is this is just on the boundary. In this point, these two circular orbits merge, and you have this circular orbit. And if you are here, you will be pushed and you will fall into the black hole. And if you have less angular momentum, there is no circular orbit at all. And now this circular orbit is at 6 gravitational this is the relevant one. This is the one that you have to see. This circular orbit is at 6 gravitational radii for Schwarzschild metric. And for the Kerr metric, if you add rotation, then you have to add the Kerr parameter. This now depends on whether you are prograde or retrograde relative to the motion of the black hole. It will go all the way to the horizon at 1 if you are moving, if the particle is moving in the same direction of the black hole, and it will go up to 9 gravitational radii if it's going in the counter direction of the black hole. So this, if you want to rotate around the black hole, then this is the last place that you can do it. And depending on the A over M, on the ratio, you can do it closer or farther from the black hole. But this has a very deep, very immediate and important physical implication. This is an artist concept of how an accretion disk around the black hole looks like. I once gave a popular talk here in Jerusalem, and after the talk, one of the mathematicians came to me and told me, Tzvi, I'm really amazed that you can have such a fantastic telescope that you can see this picture. So, not yet. This is the companion star. This is the star is taking, grabbing material. It's filling its Roche lobe, so it's grabbing material from material from the star falling onto towards the black hole. It has too much angular momentum, so it's rotating in a disk. The disk is dissipating the angular momentum and energy. So in this disk, actually, there is matter flows in, angular momentum flows out, and energy which is dissipated is radiated away. And this is what we see. This is the X-ray source that we see. And you can just use, yes?
How narrow are these jets?
The jet is not relevant right now for this discussion, but the jet that may or may not come from the center is about 5-10 degrees. But that's a different story. I may get to the jet towards the end of the talk. If you look at the disk, you can use your Newtonian intuition, realize that once you get closer to the black hole, the potential is deeper, so you dissipate more energy, and this is reflected by the spectrum. You emit X-ray in the innermost region, UV farther out, and then visible and infrared in the outskirts. So there is a temperature gradient here. And there is a beautiful theory for this kind of disk, which is a thin accretion disk, which was worked out by Shakurai and Sunaev in the early 70s. And I never know if this was independently or just or not. Immediately after that, Kip Thorne and Novikov published a fully relativistic version of this accretion disk theory. So we can use this accretion disk theory. There is a fudge factor alpha that for some reason that we understand now is working, and we can try to fit the model of the spectrum of this, and these are fits done by the group at Harvard. Actually, many of the pictures here are from the Harvard group led by Ramesh Narayan, but since he's working with various collaborators, it's almost the first author which is there. But you should have the name Ramesh Narayan in mind in many of these ideas which are here. So this is a fit of observation of Cygnus X1 in X-rays in different times. You see the observations, you see the theoretical fit, the different lines correspond to different components, and this is how good the fit is. So if the line is exactly 0, this means that the fit is perfect. You see there is some noise here, but the noise is not very large. And using this fit, what they do almost in a machine. Oh, my chairman is going out, so I'm in a fantastic position. I can talk as long as I want. Oh, you just came. Too bad. Okay, but so what they do is now they fit the model. And if you remember what I said before, the innermost part of the disk depends on the rotation, on the mass of the black hole. If the mass is larger, it's farther out because simply the gravitational radius is larger, but also on the angular momentum. So by fitting this model, you can figure out basically where is the innermost part of the disk. And by figuring out where is the innermost part of the disk, you can measure the parameters of the black hole. And there's almost a small industry there doing that. I just show here for this analysis for three of the systems. So Cygnus X1 is here. You see that the mass is 14.8 plus or minus 1, just right where we expected it from the dynamical argument. So this is consistent. And there is no known object that we can put in this mass range apart from a black hole. But who knows, they may be surprised. But they also measure the A parameter, and the A parameter is 0.983. So it's rotating almost very fast, but it's not, of course, it's not 1. It couldn't be in principle 1, but it's very close to 1. These are two other objects which have been measured with high precision. You see the masses 31, 70, and these are also the rotation velocities. And here is from another picture from the same group, from the compilation of the same group. What you see here, just to give you the scale, this is the distance from the Sun to Mercury. If I would take the distance to Earth, it would be somewhere like this. So this is the scale of our solar system. And this is about 13 known systems plotted to scale of the companion star and the black hole and the disk. So this is how, this is a theoretical picture. It did not come from direct from the observation, but this is how, from learning from the spectrum, what can we say about the system. We can also measure the inclination. I forgot to mention that there is this inclination parameter, which is unknown, cannot be determined by the dynamics. But when you do the fitting, you can also measure the inclination parameter. So you can see, for example, this is a large system, still small compared to the solar system, yes? This is the accretion disk around the black hole. This is the companion star, which is distorted, and it's shedding matter here. This is Cygnus X1, the one that I said before, with a separation which is smaller than the distance between the Sun and Mercury. And this is various other systems, which have, all of them are emitting X-rays, and all of them are, all the objects which are here are solar mass black hole candidates. Now there is a question, is there or is there no horizon there? How do we know that there is a black hole? Now, there is a good argument that there is horizon there. Or there no horizon actually is yes horizon. No horizon is for the other systems. So you can, what you see here is the luminosity for different systems. This is this is just the axis here is irrelevant. It's just the orbital period. It's not relevant at all. But each of these objects is a different system. And what you see here, all the guys which filled circles are black hole candidates based on mass estimate. And these guys with open circles are neutron star candidates. And this is the minimal emissivity. And you can see a difference here. Apart from this guy, and also if you include this guy, there is typically a factor of 3 in luminosities, in the minimal luminosities. This is the luminosity when the system is very quiet. And there is a good explanation to that, which is the ADAF explanation. And this is that at a very low accretion rate, when the system sometimes goes a period of very low accretion rate, there is very small mass transfer from the companion star, then the accretion disk that we saw here, this kind of accretion disk, become very different. It become inefficient. And instead of radiating the energy that it is producing, it is carrying the energy inwards. And this is called ADAF, for some acronym, which just reflect the fact that the energy is not transmitted but transported inwards. And the energy that is transported inward is lost. It's not seen by the observers. But there is a big difference here. Because if you have an ADAF around a black hole, then everything will go into the black hole. On the other hand, if instead of a black hole you put here a neutron star, then eventually things fall on the neutron star. Things will fall on the surface of the neutron star, and you could not avoid releasing the gravitational energy from the last impact of the matter onto the neutron star. And this is why you expect that in neutron stars, in case of very small accretion rate, you will have a much higher emissive luminosity than neutron stars, and this is actually what you see here. So you can take it as an evidence for existence of horizon in these systems, which allow you to swallow everything, and in contrast to this neutron star system. And the dichotomy is very nice. I mean, the identification of the black holes is not done by the luminosity, is done by a very different idea. This is another object. This is one object which is not so nice. It's emitting too much energy. Okay, one comment about these black holes, which is not really related to astrophysical black holes, but it is related to what we heard before in Gary's talk, and it's related to the inner structure. These black holes are rotating, and if they are rotating, if you think about the maximal extension, then it will be something like this with towers of connected regions. And there is this Cauchy horizon. This is the black hole horizon. There is this Cauchy horizon that sits here. That when you try to cross to the higher universe. About 16 years ago, nobody have done this exercise for a real rotating black hole. But for the analog charged black hole, not maximally charged, but just charged, we have done this exercise 16 years ago of actually evolving this dynamically and solving the reaction of the black hole to the matter which is to the charged matter which is falling into it. And to make a long story short, what you see here, that this is the mass of the black hole as measured on the Cauchy horizon. And this mass reflects the Riemann tensor there. And you see that this is the line of the mass. And you see this very, very nicely, that the mass diverges there, which means that the Cauchy horizon here becomes singular in a realistic collapse. So this is a beautiful idea that you can go through a black hole to a different universe. Personally, don't try it. This is my suggestion.
But why did you do it? Because there's no...
Excuse me?
Why did you do it? Because there's no astrophysical application.
I'm doing also something which are not astrophysics. Okay, if we go back to Laplace, Laplace was talking about very different black holes. You can convert to GM over R equals C, GM over R equals C squared equation to a relationship between the mass of the black hole and the effective density of the black hole. Now, Laplace, when he was talking about black holes, he was talking about objects with a density of 1. If you put, this is typical, this is what you have here on Earth, and this is also the average density of the sun. So this is sort of reasonable density to think about 1 gram per centimeter per cubic centimeter. If you plug 1 here, you get that for 1 gram, the mass of the black hole that you get is about 10 to the 8 solar masses. It's very different from what you have here. Here we have black holes of about 10 to 20 solar masses, but very different from this. So this was very different from what we said before. Actually, Laplace was criticized about this idea of black holes, and there were 2 arguments against it. One was a theoretical argument, is that how do you know that light is actually attracted by gravity? There was no evidence for it. But the second argument was that this is nonsense. We know that there are no objects of 10 to the 8 solar masses. So I don't know which one was more convincing, but the fact was that he took out, as far as I know, he took out the idea of black hole from the second version of his book. This was like what we do today in addressing the referee comments. Yes, we. So it was. Hmm? So this was not there in the later editions, but this was the prediction. And
what is the date of the second edition? What is the date?
I don't know the details of that.
But the alternative explanation is that the wave theory of light that become established.
Yeah, it was possibly that it was because of the wave theory rather than this argument. But this was also one of the arguments. Okay, so this is the center of the galaxy in visible light. And actually, it's a very, it's not an easy place to observe. It's very beautiful, but it's difficult to observe it because it's full of these dusty lanes. And this dust makes it very difficult to explore what is exactly inside. And we have to wait for advances with infrared technology to explore using infrared what is exactly in the center of the galaxy. And not only infrared, we have to use infrared plus adaptive optics. And this is kind of a public relation picture from UCLA showing how this is done on Keck. And this is not, the idea of this laser is not to shine all the way to the center of the Milky Way, but it's just to make an artificial star here at the top of the atmosphere. And with this artificial star at the top of the atmosphere, you calibrate your adaptive optics to focus, to manage to overcome the obstruction of the atmospheric obstruction and to see better through there.
This is what is used for exoplanets?
Exoplanets? No, not as far as I know, but it's essential here. And the two groups who are doing it, one at UCLA and one at Max Planck, have been heavily using this technology. So this is what they discovered. And I have here the drawings from the UCLA group, just because they are more easily accessible on the internet. But you have similar things from the Max Planck group. This should be. Oh, this is not so nice. Okay, there was supposed to be a movie here, but it's not working. Oh, it's working. So what we see here is the position of stars around the center of this point, which you just measure from Newtonian dynamics. This is the focus of the focal point of all the ellipses. And you see this is a function of time. And the first measurement were here in 95. And one circle was completed of this star, the nearest one, after about 15 years. And see, here you see the drawing of this, and here you see another drawing, which is more schematic. And so you can use very simply Newtonian dynamics to know exactly where is the center of this. And we can also measure the mass here. And the mass is 4.1 million solar masses located at this point. The nearest star, S2, is at 700 RG. 7,000 RG from the center, which means that you should begin to see a relativistic effect. In fact, more careful measurement should see a periastron shift. And the goal of the observers is actually to find nearer stars in which you'll have all kind of relativistic corrections to be measured. Just for a comparison, Mercury is about 20 million RG from the sun. So just to show you the magnitude of relativistic effects. So we know that so again, just like with the explanation for the neutron star, for the black hole with solar mass black holes, we don't know of any other object that could do this. So we have about 4.1 million solar masses. The gravitational radius of this is 8 times 10 to the 11 centimeters. And this is within 4.4 times 10 to the 12 centimeters, which is about 5 times the gravitational radius. So it's very difficult to imagine another object which will be sitting so close. And I'll show you in a second how we know this. The distance to this is about 8 kiloparsec, which is 26,000 light years. And now I can divide and calculate what is the angular size of this. So it's of the black hole. So Rg over d, if I divide, is 7 micro arc second. A micro arc second is about 10 to the minus 10. It's the dimensionless number. It's about 10 to the minus, slightly less than 10 to the minus 10. So it's a very, very small angle. It's a very small angle. And this is comparable to 2.2 millimeters across the radius of the Earth. So if I translate it, then so if I want to see this using a telescope, the angular resolution of a telescope is lambda over d. Lambda is the wavelength, and d is the opening diameter of the telescope. And if I do this calculation for optical wavelengths, the size of the telescope should be about 200 meters. Now you understand why we need large telescopes. They're still cheaper than the next large collider, but
Not 200 meters.
so what we need to do is to observe something like 2.2 millimeters from from the other side of the Earth, and this is actually the next size of telescope that are going to be built. They are not 200 meters; they are 30 meters. So it's beginning to get there.
What are the nature of limitations by atmosphere? Because
The atmosphere, you manage to get most of it by adaptive optics. All these large telescopes
so
are.
it means that from atmosphere there is no bound of the resolution.
The old bound of the resolution from the atmosphere was about 1 arc second, but we go much below it by now.
So this adaptive also.
Yeah, the adaptive optics takes it down. Yeah.
Then what is the reason to go to space? One of the main reasons.
Well, it's an interesting question.
Ultraviolet, infrared.
Yeah, first of all, there are different wavelengths that you cannot, that the atmosphere simply absorb. Especially if you want to go to high redshift, you have to go to infrared, and this is completely absorbed in the atmosphere. But there are also, but personally, I still remember the days that you saw a picture of what can you do from Earth and what can you do from the Hubble Space Telescope, and to see how this improved. There were 2 pictures how it is improved, and that later on I was old enough to see a similar picture with what you see with the Hubble Space Telescope and what you can see with adaptive optics, and the adaptive optics can be better. Because the telescope is larger, and if you get rid of the atmospheric problems, then you win by this factor of d. There is a limit to what can you send to space. But there is an alternative. You don't have to go to optical. In the radio, you lose on the wavelengths, but you can gain a lot in the aperture by the fact that you can use VLBI. So we know how to correlate. I don't know, but astronomers know how to correlate 2 radio telescopes. And if you correlate the 2 radio telescopes, you can have effectively a single telescope with an opening of few thousand kilometers. And now it's becoming interesting, because you remember that I've shown there that this corresponds to 2.2 millimeters at 6,000 kilometers. So if you do observation at this wavelength, which is upper range of the radio, you can actually get close. And in fact, just on 2015, this last one of the first paper that I saw on the archives was observation of the Harvard group with the people from MIT and others on using a radio telescope reaching levels of about of less than 5 gravitational radii from the center of this black hole. This is how we estimate the size of about 4.4 that was mentioned before. So this is at the center of our galaxy. It is not the only guy. This is the largest nearby black hole. It sits in M87. It's a large nearby galaxy. And what you see here that it emits a jet. We see this is the jet. This is an enlargement of this region. And the black hole is here, the center of the galaxy. It's slightly offset from the center of the galaxy. And we can do the same calculation for this guy. This guy is 6.2 times 10 to the 9 solar masses. If you remember the previous formula, for the density, the average density here is 0.01 gram. So it's, I cannot say that it's thinner than air, but it's definitely thinner than water. It's a black hole. The gravitational radius is 1.9 times 10 to the 15. So it's much larger than the distance between the Earth of the Sun. It's actually even larger than the distance from the Earth to Jupiter. It's really huge. And the distance to it is only 16.7 megaparsecs. So now it's a different ballgame. It's much farther. But because of some cosmic coincidence, the RG over D, the distance, the ratio between the gravitational radius and the distance is comparable. It's also a level of few milli-arc seconds. So it is slightly smaller. You need here a slightly smaller object, but still comparable. And the same observation was done towards this galaxy by the same group. And what you see here is a simulation on the left-hand side. This is what the black hole will, how the black hole will influence the light around it. Earlier on, I showed the black hole as a black point over a background, but this is not correct. This is incorrect because the black hole will distort the region very close to it. And this is a picture of the distortion. The gravitational field of the black hole is acting as a gravitational lens, a very strong gravitational lens, and actually focusing some of the light and deflecting some of the light away. So you see this region is dark and this region is very bright because of this deflection. And this depends, of course, on the mass of the black hole, but also on the rotation of the black hole and the direction of the rotation of the black hole. So this is a simulation of what should happen. And this is some measurements. And these are some two models. What is important to take here, we don't have this, we are still far from here. We are not here yet, but we have measurements which are on the scale of about 5 gravitational radii, both from the black hole at the center of our galaxy. We have radio measurement, and from the black hole at M87. So, and if you remember, this is deeper than the marginally stable orbit of a Schwarzschild black hole. It will be farther, which is at 6 gravitational radii. So we are getting very close to the horizon. We don't see the horizon yet, but we are getting close there. Now, black holes have very closely related to their galaxies. And in fact, this is one of the most active field of research now. Avishai that left is doing quite a lot of work on that, but he's not the only one. Everybody is doing this kind of work. And from an observational point of view, it was realized that the mass of the black hole is closely related to the bulge. This is what was missing in Jim's peculiar galaxies. There were no bulge. You're puzzled why, how can you make a galaxy with no bulge? My guess from here that this galaxy does not have a black hole in the center.
The Milky Way has a black hole.
No, but the Milky Way is a bulge, small bulge. It's on the it's on a Magorian relationship, more or less.
But it doesn't have a color. It has a pseudobulb.
Hmm?
It's fine.
What is important is that there is some mass at the center of the region here. This mass is not as comparable to the total mass of the galaxy, but it's a significant fraction of the mass of the galaxy. It's a few percent of the mass of the total galaxy, and it is much more than the mass of the black hole, which is inside. But somehow, surprisingly, there is a very close relationship, which you can see plotted here on two different curves. And I will not go to explain what does this quantities mean. Sigma is actually the velocity here, which is a proxy to the mass of the system. And this is the luminosity in the strand language of observers. And you see in both cases that when you have more massive black hole correspond to faster velocities, which means larger bulges and more luminous bulges. So there is a relationship between this bunch of stars here and the black hole, which is in the center. And there is also, it's also a critical part of galaxy formation modeling now is the feedback of the black hole on the surrounding galaxy. So, but it's the story is not complete yet. We know that there is a connection. One interesting connection is this concept, this issue of tidal disruption. What we see here is a simulation of a star, which there is a black hole here, which you don't see, but the star passed near the black hole. It was tidally disrupted, and now half of its material was ejected to infinity, but the rest of the material, the other half is coming back, and it's circling this black hole, and eventually will form an accretion disk around this black hole, and we will see this accretion disk. And in fact, it is likely that we have actually seen exactly such events. These are light curves from 6 tidal disruption events. They are somehow remarkably similar in their pattern. This light curve has a typical decline here, which is characteristic by t to the minus 5/3, which comes from some theoretical considerations. And so we have at least 6 candidates which are they are transient. They suddenly appear, they go up, and then they go down, and they disappear. So this is what such an event will happens, because it's a one. It doesn't happen regularly. It happens once per about 100,000 years in a galaxy. And what we see here is actually some simulation that we did of more detailed simulation of this. This is just a simulation of the returning matter. So the simulation contains only the second part, and you see the build-up of a structure here around the black hole. There are some problems with this simulation. It actually manifests that the structure that you see here is slightly different from what other people thought before. But this structure, we believe, is what is emitting these light curves that we see here. And there is some tentative agreement between the observation and the result of these simulations, but nothing as close to what.
100,000 years comes from estimating the number of stars.
This is come from estimating the number of stars in the center of the galaxies. The stars every once in a while are deflected by interaction with other stars, and they change a little bit their orbit, and they go more towards the black hole, and this is how.
Is this compatible with the number of observations?
Yes, yes. But it's very, the compatibility is not very big. It's two numbers which are extremely uncertain are compatible with each other, so we are happy. But the uncertainty in both numbers is huge. Okay, I want to jump to another topic which is important in Kerr. In a Kerr black hole, you have an ergosphere, and this is the region in which you can have a negative energy. Particles can have negative energy. And in 69, Penrose suggested that since you pointed out that you can have this negative energy orbits, so he suggested what is called the Penrose process, in which you have a particle falling from infinity, splitting into two particles within the ergosphere. One is ejected with a negative energy and falls into the black hole. The other one gets a positive energy and escapes to infinity. So this could be very interesting both from astrophysical and from potentially technological concept. This was a visualization of how future civilization can use this. So these guys are sitting around the rotating black hole, and they actually extract, this is very clean. They extract the energy from the black hole. They take their garbage, throw it to the black hole. The garbage goes to the atmosphere, split to two parts. You see these parts go with a negative energy, eject it back with positive energy, and this comes back to here, rotate the turbine, and this turbine generates electricity. This is the dream of every green party.
Did you write application already?
Well, unfortunately, my PhD was to show that it doesn't work. The trouble why it doesn't work is that to do this, you have to eject the garbage here in the rest frame of the container at roughly the speed of light. And you have to convert significant fraction of the energy of the container to energy in the rest frame just to do this. Now, if you are so sophisticated and you know to convert 50% of your energy, of your mass to pure energy, you don't need all this extra 5% that you get here. You just sit here quietly on your surface and you convert mass to energy, and you are very happy with it. So this is why this is the, it's good to sell it to politicians, but not good from an astrophysical point of view or so on. But there is an alternative, and the alternative is the following. If you take two particles, and now let the two particles collide inside the black hole, this is more interesting, because now in the collision you can have as much energy as you want. These two particles come and fall from infinity, and now you can actually get energy gains, and you can try to estimate what is going on here. There was an unfortunate paper in the in PhysRev letters from a couple of years ago claiming that you get infinite amount of energy here and suggesting that this is the way to build the future accelerators. Don't build on it. If you want to get to very high energy, you should try to find some other ways. It doesn't work, but there is an analogy of this process, which probably works in astrophysics. And the analogy to this process is the electromagnetic analogy, in which we, instead of these particles and mechanical flux that goes into the black hole, we use a magnetic field, and the magnetic field actually can engulf the black hole and can extract energy from the black hole. And what I want to show here is a simulation. I hope this works. So what you see here is a simulation. You have here a rotating black hole. You have the inner region of an accretion disk, and this is a side view, and this is view from the top. And the lines here are magnetic field lines. And you can see the magnetic field getting into the black hole, and you can see this jet. You remember somebody asked me about the jet before. So you see the jet coming out from this. And what you see here is the rate of energy extraction. And the most important thing is actually the curve down below here, because the curve down below here measures the energy which is escaping to infinity divided by the rate of mass inflow into the black hole. So it is energy output divided by the mass input. And if you look at this, you find that this is 100%. So this value, at least in this idealized simulations, gets above 100%. The meaning of this is that, like this imaginary civilization, we're actually tapping the rotational energy of the black hole. So we take the rotational energy of the black hole, we slow down the black hole, and in this process the black hole is slowed down, and we are extracting energy. And this is, we don't really know if this is the way to get jets from black holes, but this is the best way that we have so far. And it may be that the jet that we saw here in another system, like in M87, this is what we see here.
I thought accretion spins up the object.
The accretion spins up the object, but at the same time, the jet, which is taken out, is extracting even more angular momentum. So the net result is that it slows down. If you don't have the jet, the accretion will speed up the object. Okay, I'll try to, in the last 5 minutes, to quickly talk about 2 other topics which are rarely mentioned. One is polarization in Kerr. Keep mentioning in this talk that you have trajectories and you have a parallel transport about this trajectory. And if this is the trajectory of a photon, the photon will have its polarization. And as you parallel transport in a curved way, the vector of polarization, which is perpendicular to the direction of the photon, will be shifted. And now it is shifted in a very interesting way in a Kerr. And especially if you are near to the black hole, it's shifted more than if you are far away from the black hole. Luckily, there is a beautiful mathematical construction to calculate it using what is called the Walker-Penrose constant, which is based on a spinor. But this is another constant. It's actually a complex constant, which is satisfied along the trajectory. And it satisfies a relationship between a wave vector k of a massless photon and a vector f, which is perpendicular to this massless photon, which is actually the polarization vector of this photon. So by solving this, we can actually measure the polarization of light or estimate how the polarization of light will be transformed in propagation in Kerr without doing much computation. And we have this kind of curves. And this is a system in which you have the Newtonian polarization. This is just the angle of plane of polarization as function of energy. In a Newtonian case, it will be constant. And this is for 3 types of black hole. And you see this change. And the change is because, again, when you go to higher energies, then the photons are emitted from nearer to the black hole. So they are rotating more strongly. And so by measuring this kind of polarization pattern, we can also learn about the detailed metric in the vicinity of the black hole. Now, you have all seen this satellite, which is called GEMS, which was designed to measure exactly this effect. And it vanished like this. Kip mentioned earlier that Lisa was one of the victims of JWST, the new space telescope. This is also one of the victims. It was already approved and disappeared completely forever. So it will take some time to measure this. Mind you, well, you're all theoreticians, so you don't have to worry about this. My personal suggestion, if you're a young person, don't try to build an X-ray polarimeter. There was a huge X-ray polarimeter built in the 80s in Columbia to be launched on a Russian satellite that never took off. And this was the second polarization mission since then. And so if you get an offer to be on such a mission, think twice. The last topic is how do we really know that there is a black hole? And in my mind, the only way really to know that there is a black hole is to measure the existence of horizon. And to measure the existence of the horizon, the only way that we can do it is using gravitational wave that will reflect the quasi-normal mode of the black hole. And this is the first numerical simulation of this kind of effect. What we see here is actually calculation from the 80s of rotating collapse to a black hole. And the black hole forms here. And these are the oscillations after the black hole forms. And this fits perfectly well to the lowest modes, or the lowest quasi-normal modes of a black hole. So how do we know that the black hole formed? We have to see this. The question is, how do we see this? And we already heard about the possibility from Kip about neutron star mergers. In '89, we suggested that in addition to being perfect source for gravitational waves and neutrinos and the formation of a black hole, these mergers will also be sources of gamma ray bursts and R process material. R process is heavy elements which are not produced otherwise. So this was the suggestion. This was confirmed by a paper in New York Times, and as you all know, everything which is published in the New York Times is correct. So what they describe here is the following, that following on this movie, It's a Wonderful Life. So in the movie, It's a Wonderful Life, they sit in the bar and the bell ring, and the angel tells to Clarence, you know that every time that the bell ring, an angel is formed. So the analogy here is that every time that there is a gamma ray burst, a black hole is formed. So this can be formed either in a collapse or in the merger like this. So a gamma ray burst is possibly a very good way to tell that we have a black hole form. And so the conclusion of this is actually shown here in this movie. How will we know that a black hole really formed, that we'll identify a black hole, is one day we'll see a neutron star merger like this, and we'll see the merger. We'll see the gravitational waves coming from this merger, and then we'll see the gamma ray burst which is accompanying it, so maybe it will enable us to identify it, and this may be the possible identification. Thank you.